Alright, let's get started. I'm going to walk you through how to draw a schematic step by step. First, we head over to the website EasyEDA.com. Once we're there, click on Design Online and make sure to select the Pro Edition, not the standard one. Then we hit New Project. Give it a name and hit Save. The project link is automatically generated, so we don't need to worry about that. By default, the system will generate three things for us: a board, a schematic page, and a PCB layout. We're going to double click on the schematic sheet to open it. Now, what we see is basically an A4 size drawing sheet, and everything we do will happen right here. We're going to complete the whole schematic on this sheet. First, we need to search for the parts we're going to use. So how do we find the parts? Well, first, we need to tidy up the view a little just to make drawing easier. Looking at the circuit from left to right, first part is just a startup circuit. Let's go back to the BOM table we prepared earlier. Right here, we've got a 10K through-hole resistor listed. Just copy the part number that we prioritized in the BOM. Back in EasyEDA, click Place and then Device. Or use the shortcut key. It's Shift plus F. Quick tip: even though we are using the Pro edition of an EDA tool, the short keys I'm using is actually from the standard edition. That's just my personal habit. I'm more used to those. If you want to change your shortcut keys too, just go to Settings and you can either switch to the standard set or customize your own. If you're not using the STD version, then your shortcuts might behave differently. Alright, let's get back to the schematic. Paste it in the right part number, search, and boom. Here's our 10K resistor. You will be able to see some of its parameters here, like resistance value and pricing. Click Place and drop it onto your schematic. Once it's placed, you will need to bring out the related I/O pin from the microcontroller. To do that, go to Place and Net Label. Hit the Tab keys to quickly name the label. The rest of the components will follow the same steps: place, wire, and label. Next up, on the left side, we've got our 3.3 volt power. Now, instead of using a net label, we're going to use a net flag. This is a special symbol used to mark a power that like 3.3 volt or GND. Just like before, hit tab to rename the flag. Change it to plus 3.3 volt. You can also just click the text directly to rename it. Both ways work. For drawing wires, go ahead and click the wire tool, or just hit the W key. That's my go-to shortcut. Depending on your settings, your shortcut might be something like Alt plus Control W, so take note. Once everything is connected, power, resistor, I/O pin, and ground, that's it. Startup circuit is done. Alright, now let's move on to the ESP8266 main controller part of our circuit. Here's what we need. First, 10 ohm capacitor. Second, a 100 NF capacitor, and the ESP8266 chip itself. Let's go ahead and search for these components in the same way we did earlier. Click Place, then Device, or press Shift plus F. Use spacebar to rotate components while placing them. Super handy. Once we've placed everything, next we need to bring out the I/O pins from the chip. You can totally do this the traditional way, draw wires from the pins and add labels one by one. But there's a much faster way. Select the ESP8266 chip and click on Fan Out Net Label from the toolbar. A little window pops up. This is where we can enter our pin names under net name. Once you type them in and hit confirm, EasyEDA will automatically add those net labels next to chip pins. Pretty neat, right? And of course, just repeat this for the rest of the I/O pins. Make sure the net names match your schematic design. Consistency is key. Now let's talk about VCC. This is our 3.3 volt net label. Same as we used before with the net flag method. Pay attention here. C1 is an electronic capacitor, which means it's polarized. The positive side goes to 3.3 volt and the negative side to GND. C2 is a ceramic capacitor, so it doesn't have polarity. You can place it either way. If you mix that up, the electrolytic capacitor could be damaged when power is applied. So always double check. Now, for any pins on the ESP8266 that we're not using, you'll want to place a no connect symbol on them. This is really important because if you don't, you'll get DRC errors when you go to validate your schematic later. So just go through and add those NC symbols where needed. To keep our schematic organized and readable, we're going to group sections using rectangles. Click Place, then Rectangle, and draw a nice border around the ESP8266 part of the schematic. Then, add a label using place and text, and name it something like ESP8266 main control. You can adjust the font size to make it easier to read. Let's move on and draw the button circuit and the ADC voltage sensing part. Start by finding the push button component. Once it's placed, feel free to move it around a bit to make room. Just tidy up the layout as you go. Now, one leg of the button needs to connect to plus 3.3 volt. Here's something you need to know about button pinouts. Pin 1 and pin 2 are internally connected. Pin 3 and pin 4 are also connected together. But two sides are not connected unless the button is pressed. That's what gives us switch functionally. So don't make the mistake of wiring pin 1 to pin 3. If you do that, the button will always be conducting, which totally defeats the purpose of having a switch. For the two unused pins, go ahead and mark them with NC, which is no connect labels. This way, your schematic stays clean and error-free. Once that's done, add a rectangle around this part and label it, something like button input. Now, we'll add a simple voltage divider circuit to feed a scaled down battery voltage into an ADC pin. We need 175K resistor, one 10K resistor, find a 75K from the library. In between the two resistors, we place a net label for the ADC input. Then, connect a wire from this midpoint to the ADC pin. What this does is it divides the battery voltage by about 8.5 to 1, which makes it safe for the ADC to measure even when the battery is full. Now, let's build the servo motor interface. We'll have 4 servo headers, U4, U5, U6, and U7. Each one uses a 1x3 pin header. The wiring is the same for all 4. Pin 1 equals to GND. Pin 2 equals to plus 5 volt. Pin 3 equals to IO pin, connected through a 10K pull-down resistor to GND. Search for the 1x3 pin header, place it, and wire it up. Once you've built the first one, use Ctrl+C and Ctrl+V to copy the whole servo module. It makes life so much easier. Now, this next step is important. You must assign different I/O pins to each servo. If you leave them all on the same I/O pin, you'll end up controlling all 4 servos at once, and that's definitely not what we want. So after pasting, go through each servo block and update the I/O net label to a unique name. This part really matters for later control logic. When you're done, draw a rectangle around these 4 blocks and label it servo interface. Now let's move on to the power regulation circuits. First up is the 5-volt linear voltage regulator using the AMS1117 5.0 chip. Search for the AMS1117 5.0 and place it into your schematic. Important note here, our project actually uses 2 LDOs, one to convert voltage down to 5 volt and another one to drop it further to 3.3 volt. These are 2 different chips, so don't mix them up. Mixing them will mess up your power rails, and if the power is wrong, the whole board is not going to work, guaranteed. So the 5-volt circuit looks like this. VBAT goes into the input pin, output is plus 5 volt, add a 10 capacitor on both input and output sides, typical for LDO stability. Once it's wired up, go ahead and draw a big rectangle around it and label it as something like 5-volt rectangular circuit. Now we move on to the 3.3 volt LDO. Again, search for the right chip, probably something like AMS1117 3.3 or equivalent. Now here's the thing, the circuit layout is basically the same as the 5-volt version. Once it's done, group it with a rectangle and label it as 3.3 volt regulator. Now, let's wire up the OLED display, the OLED display. We're using a 0.96 inch OLED module. It's a super common and uses the I2C interface. Search for it, place it, and connect the GND and VCC pins. You already know the drill. Now for the I2C lines. SCL for the clock and SDA for the data. Each of these need a 10K pull-up resistor to 3.3 volt. So place two 10K resistors, one on each line, and wire them up. Here's something important. On I2C buses, the connection must not have junction dots where it shouldn't be. Make sure your wire connections are clean. No accidental short circuits. Once that's all done, group the screen and its pull-up resistors with a rectangle and label it like OLED display plus I2C, for example. Next, let's add the programming header. This is a 1x6 pin header spaced at 2.54 millimeter pitch. Super common. Place it and then bring out the following wires. First, GND. Second, IO0. Third, 3.3 volt. And lastly, another GND. Also, bring out the RX and TX too. RX and TX are the serial communication pins. We use these to flash firmware from the computer to the microcontroller. Wire them accordingly and double check the RX from your USB to serial converter goes to TX on the chip and vice versa. Once the section is done, put a rectangle around it and label it Download Interface. Now, let's add the power switch. We are using a part with the label C, and it has multiple pins. Here's how we wire them. Pin 4 and pin 5 goes to GND, pin 2 and pin 3 connected to voltage. Pin 1 is unused. Leave it floating. Why wire it this way? We are using a switch to control power from the battery to the voltage regulators. So VIN is the raw battery voltage coming in, and we'll label the output of the switch as VBAT. This goes to the input of the LDOs. In other words, the switch acts like a gate to turn the power system on and off. Next, let's add an expansion header. It's a 1x3 pin header carrying 5V, VIN, GND. You can either look it up or just copy one of the Servo headers, since it's basically the same thing. Group the switch and expansion port with the rectangle and label it appropriately. Alright, so far we've been using parts that are already available in EasyEDA's component library. But now, we're going to create a custom part from scratch. In this case, it's an AA battery holder. Why do we need to do this? Well, certain parts, like the battery holders in Servo models, might not be available in the standard LCSC library. So if we can't find them using part numbers, we have to draw them ourselves. Let's start with the schematic symbol. In the upper left corner, click File, then New, then Component. Name it something like AA battery holder and click Save. Now, we are in the symbol drawing workspace. It's a blank page. First step, change the grid size. By default, it's set to 0.1 inch, but our standard schematic uses 0.05 inch, so change it to match. This keeps everything aligned properly. Now, we'll draw the battery symbol using simple lines. Just click Place with a polyline and draw. one long line and one short line. That's one battery symbol. Repeat it to represent two AA batteries in series. Next, we'll place two pins, one on top, positive, and one on the bottom, negative. That's it, your symbol is done. Hide unnecessary text like names or values. And scale the lines down a bit. Maybe set thickness to 0.1 to keep it neat. And remember, in the battery symbol, long equals to positive, short equals to negative. Now, it's time to draw the footprint or physical layout of the AA battery holder. Click File, then New, then Footprint. Give it the same name, AA battery holder, and hit Save. We're now in the footprint editor. So how do we know what size to draw? It's really easy. Just find the datasheet or product listing for the battery holder you're going to use. Look for the mechanical drawing or dimension diagram. It will tell you the length, widths, hole locations, and so on. Make sure to choose a model that has mounting holes. That make it easier to fix the holder onto your PCB using screws. But even if your battery holder doesn't have holes, no worries. Just focus on pin positions, which are the battery terminals. Let's start with the outline. Select Place, then Graphic, then Rectangle, and switch the layer to Top Silk layer. This is a silk screen. Based on the diagram, draw a rectangle. X start, 29.755. Y start, 16.464. Width, 59.1 millimeters. Height, 32.92 millimeters. And line width, 0.254 millimeters. Don't stress about being exact down to the tenths of a millimeter. Better to draw it slightly bigger than too small because the tight fit can cause problems during assembly. The battery holder has two terminals, one positive, one negative. Select Place the pad and choose Single Pad. Set the pad type to multi-layer and shape to oval. For pad 1, width is 1.6 millimeters. Height is 3 millimeters. Drill type is slot. Drill diameter is 1.5 millimeters. Slot length is 2.3 millimeters. Coordinates: x equal to negative 27.165 and y equal to 7.5. Once that's played, copy it and make pad 2. Be sure to change its number to 2 and update its coordinates. Don't forget to rename the pad numbers. If both pads are named 1, it will cause errors later. If your holder has mounting holes, we can draw them too. Use Place and Slot and choose the round slot area. Draw two of them. First, center x equals to 0, y equals to 9, radius equals to 2 millimeters. The second one is going to be center x equals to 0, y equals to negative 9, and radius 2 millimeters. Now, to avoid confusion during assembly, it's good practice to add a plus and minus sign next to the pads. This helps clearly indicate pad 1 is positive and pad 2 is negative. When you're done, hit Ctrl plus S to save. Schematic symbol and footprint are done. Now we need to bind them together. On the left sidebar, open Lib Design. Find the component you just created and click the button next to footprint. Then choose the footprint you just made. It will be under the Personal tab. Click Confirm, and now they're linked. Save it again, go back to your schematic sheet, and in the library bottom left, find the Personal section. Locate your new AA battery holder and click Place to use it. One last note and reminder, in your schematic, the positive terminal is VIN. Because it connects to the power switch to control battery power on the board. Don't confuse this with the VBAT. Alright, now we've come to the final stretch. We're going to create a custom component for the servo model. This isn't an actual electrical component with pins, it's more like a placeholder or mechanical reference. It shows up where the servos will be installed and how much space it will take up. Let's jump into it real fast. First, go to File, New, Component. Make it something like servo model and hit save. Now we're in the symbol editor. The symbol is purely visual, so we won't be adding any pins. Let's keep it super simple. Use place, polyline to draw a basic box outline. Inside it, draw a large capital M. This represents the servo motor. You can also add a circle around the M just to make it look nice. Shrink the size if necessary. Adjust the thickness or line to space and keep it clean. No pins, no labels, it's just a reference number. Once done, hit Ctrl S to save the symbol. Next, click File, New, Footprint. Give it the same name, servo model, and hit Save. This time, we're going to draw the actual dimensions of the servo physical body, just like we did with the battery holder. You can usually find the servo's dimensions in the spec sheet. If not, take a ruler and measure it yourself. That works too. Let's draw the top silkscreen rectangle. Layer, top silk, go to Place, Rectangle, and use these values. Start X is at 0, start Y is at 22, start width at 32 millimeters, height at 22 millimeters, corner radius 2 millimeters, and rotation 0 degree. Now we've got a nice silkscreen outline that matches the physical servo size. No pins, no pads. Again, this is just to mark where the servo goes. Save with Ctrl S. Let's bind the symbol and footprint. Open Lib Design, find the servo model that you just made. Click the footprint link and choose the footprint you created. Click Confirm and save it. Now go back to your main schematic. From the Library and Personal tab, place 4 of these servos. Servo 1, 2, 3, and 4. Draw a rectangle around all 4 and add a text label, something like servo model. This gives us a visual reminder in both schematic and PCB layout of where the servos are going to be mounted. At this point, your schematic is pretty much complete. Let's do a quick recap of what we've got. Power supply circuits, main controller, input button, and ADC voltage sensing. OLED display with pull-ups, UART programming header, power switch, and expansion ports. Lastly is the custom AA battery holder, the servo interface with pull-down resistors, and lastly, the custom servo models for space planning. Don't forget to run a DRC, which is the design rule check, before moving on to the PCB layout stage. Fix any unconnected nets or floating pins, and make sure all the net labels matches your design intent. Once that's all good, you're ready to move on to PCB layout in the next step.